If you were asked to guess the longest rail tunnel in the world, a common answer, maybe the safe bet, is the Channel Tunnel.
It's a very reasonable guess.
But it's actually incorrect.
That's right. The tunnel that holds the record for length, and certainly one of the deepest ever built, is it's located deep beneath the Swiss Alps.
We're talking about the Gothard Base Tunnel, the GBT.
57 kilometers drilled straight through alpine rock. And what's really astounding, I think, is the scale of it relative to the nation that built it. This was all done by a country of just 8 million people.
That figure alone is something to consider. So for today's deep dive, our mission is to explore how they did it. We're going to look beyond just the engineering and get into what this tunnel represents.
You mean the Swiss approach to infrastructure, their democracy, that kind of thing?
Exactly. And the long-term vision needed for a project that's meant to last for centuries.
It's a story of incredible collective commitment. The decision was made by a national vote back in 1992.
And it opened in 2016, 24 years later.
Right. So a lot of the people who voted to fund it might not have even lived to see the first train go through. It's a generational commitment.
And it wasn't a simple project. We're going to look at the paradoxes, how they managed to drill through rock that was 45 degrees Celsius, or how they navigated a geological zone that apparently behaved like wet sugar.
And we should also get into why those Japanese tunnel experts, the masters of high-speed rail, said they came as teachers but left as students. There's something very specific that impressed them.
Let's start with why it was necessary. By the 1990s, the old Gothard route, the original 1882 rail tunnel, and the 1980 car tunnel, they were just overwhelmed.
Completely. The Alps are a massive barrier, and Switzerland is right in the middle of these major European trade routes.
So it became a bottleneck.
A severe one. You had over 1 million heavy trucks crossing the Alps every year. That meant huge traffic jams and, of course, a lot of pollution in those very narrow valleys.
I understand the idea for a deeper, flatter tunnel was actually quite old.
It was, yes. An engineer named Edward Gruner proposed the basic concept back in 1947.
So why did it take so long?
Well, back then, the technology just didn't exist to do it. The cost was also prohibitive. It was really a fantasy until the political and environmental pressures aligned with new tunneling technology in the late 80s.
And that led to the big 1992 vote.
Right. The Swiss population voted yes with 64% approval. And this wasn't just a political decision, it was a democratic commitment.
Financially binding citizens for decades.
Exactly. For a rail line that runs from Erstfeld in the north to Bodio in the south.
Which brings us to the money.
Yeah.
A project this long must have been vulnerable to budget cuts. The final cost was around 12 billion Swiss francs, which is over budget.
It was. But the project had a dedicated funding mechanism, and that gave it incredible stability.
So how did they shield it from politics?
It was mainly funded by something called the heavy vehicle fee, a federal charge on trucks. The fee was based on the truck's weight, its emissions, and the kilometers it traveled in Switzerland. So in effect, the very traffic they were trying to reduce was paying for the solution.
That's a clever way to do it, a self-financing loop.
It is. And it created a stable funding stream that they could rely on for the 17 years of construction that started in 1999.
So, drilling 57 kilometers. The logistics of that, starting from just the two ends, would have taken forever.
It would have been completely impractical. So the solution wasn't just about power, it was about geography.
What was the trick?
The trick was to attack the rock from multiple points at the same time.
So they created intermediate access points. I see, at places like Amsteg and Cedron.
Exactly. This let them drill inwards from 4 different places at once, which cut the timeline dramatically.
And Cedron, that was a major challenge in itself, wasn't it?
It was probably the biggest technical headache. To even get down to the tunnel's depth, they had to dig a vertical shaft 800 meters deep.
So they built a mine just to start the tunnel.
In essence, yes. And the conditions down there were brutal. Rock temperatures were over 40 degrees Celsius.
And I imagine they hit water.
Immediately. They were pumping out up to 200 liters of water every second just to keep working. Just building those access points took the first 3 years.
And once they were ready, the main tools arrived. The 4 tunnel boring machines, the TBMs. They're called factories underground.
And that's a very accurate description. These things were enormous. 9.5-meter cutting heads with 62 discs made for alpine granite.
But they did more than just drill.
Oh, much more. A TBM is a complete assembly line. As it moves forward, it's also installing the pre-made concrete lining
The
segments.
voussoirs.
Right. And at the same time, it's moving all the excavated rock out behind it on these long conveyor belts. It's drilling, lining, and clearing all at once.
And all that work deep underground, it makes you think about the human side of it.
Yeah.
The miners named the TBMs, didn't they? St. Barbara and St. Agatha.
They did. It's a tradition, a way to find some moral support when you're facing those kinds of dangers every day.
Because it is still a very dangerous job.
Very. And despite all the safety measures, the construction sadly claimed 9 lives over those 17 years. There was a train derailment near Amsteg in 2005, a rock fall near Ursfeld in 2012. You can't really talk about the engineering triumph without acknowledging that human cost.
As they moved deeper, the challenges became more, well, geological. The first one was just the combination of heat and pressure.
The heat was a huge problem. At the deepest point, you're 2,450 meters below the peaks. The rock itself is naturally 45 degrees Celsius.
But the air inside would have been hotter than 50 degrees. Impossible to work in.
Completely. So they had to build one of the most powerful underground cooling systems ever conceived.
How did it work?
They circulated chilled water through a 160-kilometer network of pipes along the tunnel walls. It was a massive undertaking, just to keep the temperature manageable.
And what about the pressure? You had an analogy for it.
Well, at its peak, the pressure was about 2,500 tons per square meter. The easiest way to visualize that is to imagine stacking 25 blue whales on every square meter of the tunnel.
That's an incredible amount of force.
It is, and it meant the concrete lining had to be exceptionally strong, often reinforced with steel, to withstand that constant weight for centuries.
But the real geological nightmare, the great fear of the project, was something called the Piora Zone.
Yes, the geologists were terrified of it.
Why? What was it?
It's a formation of what's called saccharoidal dolomite, and the name hints at the problem. Saccharoidal means sugar-like.
Okay.
When this rock is under immense pressure and it gets wet, it loses all its structure. It essentially becomes a slurry, like, as they said, a bag of sugar underwater.
So if a TBM hit that, it could have been catastrophic.
An instant collapse. The machine and the crew would have been buried, so their strategy was extreme caution.
How'd they manage it?
They were constantly drilling hundreds of meters ahead of the TBMs, taking core samples, analyzing the rock. They managed to route the tunnel around the worst of it.
But even the adjacent sections were difficult.
Extremely. In that one sector, it took them 6 months just to advance 150 meters.
6 months for 150 meters.
Yes. And a TBM in good rock normally moves about 25 meters a day. They had to inject thousands of tons of cement and resins just to stabilize the ground before they could move forward.
Which speaks to the patience required for this whole thing.
It does.
So after all that, the breakthrough moment finally came. October 15th, 2010. There must have been a lot of tension, connecting 2 tunnels drilled blind from opposite directions.
And the result was just a testament to their skill. After 57 kilometers, the horizontal deviation was 8 centimeters. The vertical was just 1 centimeter.
That's incredible. Less than the size of a coffee mug.
It's an almost unbelievable level of precision.
And that precision is what brought the Japanese delegation in 2014. Their leader, Takashi, famously said, "We came as teachers, we leave as students." What was it that impressed them so much?
It wasn't only the drilling accuracy, it was what they called the Swiss paranoid perfection when it came to the safety systems.
What does that mean in practice?
It means an incredible level of redundancy. For example, there are emergency exits connecting the 2 tubes every 325 meters. The ventilation system is hyper-sophisticated. It can reverse airflow instantly in case of a fire.
And there was also the issue of air pressure from the trains themselves, the piston effect.
Right. When a high-speed train enters a tunnel, it pushes a wall of air in front of it. That pressure change can be very uncomfortable for passengers.
So how did they solve that?
They designed the tunnel with special cross-ventilation shafts that connect the 2 tubes at regular intervals. These shafts equalize the pressure so trains can maintain high speeds without causing those sudden pressure changes for the people inside. It's a key safety feature.
Another impressive aspect was what they did with all the excavated rock. We're talking about 28 million tons.
They had a very comprehensive recycling plan. The best quality rock, the granite, was crushed on site and used to make the concrete for the tunnel's own lining.
So they reused it right there.
Exactly. And other material was used for embankments or noise barriers along the rail line.
And I believe some of it was even used for environmental restoration.
Yes, that was a really interesting part of it. The spoil wasn't treated as waste, but as a resource. In Lake Erie, for example, they used the rock to create artificial islands and shallow zones to restore fish habitats that had been lost.
So let's look at the impact now that it's operational. Passenger times from Zurich to Milan are down by about 40 minutes. But the real change was for freight.
That's the core of it. The GBT is almost perfectly flat. Its maximum gradient is only 0.7%,
And you have to compare that with the old mountain line.
which had steep climbs of 2.6%. That difference might not sound huge, but in railway terms, it's monumental.
Because on the old line, you needed multiple locomotives just to get over the top.
Correct. The flat profile of the GBT effectively doubled freight capacity. You can now have much longer, heavier trains, up to 2,000 tons, and they use far less energy because they aren't fighting gravity.
So the comparison is that one freight train through the tunnel is equivalent to taking about 60 trucks off the road.
That's the average, yes. And they even recover energy through regenerative braking on the slight downhill sections.
And has it worked? Has freight shifted to rail?
The data says yes. By 2020, about 70% of all Swiss Alpine freight was on trains. And truck numbers on that route dropped by about 30% from their peak. That means cleaner air in the valleys.
There's also a social element to this, isn't there? It's seen as an investment in national cohesion.
It absolutely is.
Right.
It fundamentally changes the connection between the German-speaking north and the Italian-speaking canton of Ticino in the south. It bridges a huge physical divide.
Which brings us back to where we started, this idea of a Swiss philosophy.
A philosophy of long-term planning, a real pursuit of quality, and a democratic process where citizens agree to fund benefits for future generations. It's infrastructure as a legacy.
The chief engineer, Lorenzo Simoni, had a great quote about that. He said, "We don't build to save time, we build for centuries."
He continued, the Romans built roads that lasted 2,000 years. We're trying to match them. It's a powerful way to think about modern engineering.
So the tunnel is this synthesis of technical skill, human cost, and this incredible democratic commitment.
The patience it required, waiting 24 years from the vote to the opening, is maybe the biggest challenge they overcame.
And that leads to a final thought for you, the listener, to consider.
Given that the GBT's success relied on this multi-decade commitment, do our current societies, which are so often focused on short-term results, still have the collective patience to build the great necessary infrastructure that our future will depend on?